Well, I want to just welcome everybody real quick to the first 2024 AI-SDM seminar session. It's great to have so many people here. We're here today with Dr. Aaditya Ramdas from Stats and Data Science and Machine Learning at Carnegie Mellon. The interesting thing about him is that on his faculty website, he has 75% data science, 25% machine learning, and somehow 20% visiting scholar. So he's 120%. That's awesome. But he's got a great talk for us. His focus is in mathematical statistics, and he's got a talk today about combining uncertainty sets. So really looking forward to it. Definitely bring your questions.
Yeah, thanks a lot, Rob. Thanks everyone for showing up on Zoom or in person. This is very fresh new work that I'm happy to present here. And it's joint work with Matteo Gasparin, who's in the last row. He is a PhD student at the University of Padua, and he's visiting CMU this semester. And this is joint work with him. It's also an archive as of yesterday. And that's the archive link if you want to follow along. We're going to probably update that next week, but you can already look at first versions. So this talk is going to be about how to merge uncertainty sets by a majority vote. It will turn out that this is an extremely basic question, and I feel like everybody should know this answer. It should be like in a basic stats textbook, but it isn't, so we have a paper on it. Okay, so what is the motivation from the perspective of the AI-SDM seminar and institute? So we have a 5-year NSF AI Institute, for those who don't know, like my visiting students over there. It's centered at CMU, but involves many other universities and partner organizations. And one of the goals of AI-SDM is to design principled methods that can allow for human AI cooperation and complementarity when making decisions in kind of resource constrained settings like disasters. And one of the foundational thrusts involves aggregating the opinions of multiple experts. These could be AI or human experts, especially when they disagree. So you have several different experts or systems providing their forecasts or opinions on what to do, or what's going to happen or something of that kind, and how do we aggregate this into making one decision or one forecast or something of that kind. Okay, so today's talk will be within that theme, and it will be about aggregating opinions or forecasts that are expressed as uncertainty sets. Okay, so very natural form of expression. So for example, for tomorrow's weather, maybe my 95% prediction set for tomorrow's snow is between 1 and 3 inches. That's mine. But yours might be different, and we might all have slightly different opinions, and how do we combine them?
Aaditya, could I interrupt you for 1 second? I'm so sorry.
Yeah.
Would you be able to turn your camera on?
Turn my camera on, my personal.
Your Zoom camera. Yep.
Yeah. Okay, 1 second. Oh yeah, I can.
Yep. And then that should be the room view. Yeah, it'll load here. Thanks so much. Sorry to interrupt.
Now I need to get that out of my way. Hold on. Okay. Okay, so anyway, that's the motivation from the AI-SDM point of view. Okay, so here's one. Okay, let me try to hide that again. I didn't know that. Invisible. Corner. Okay, here's the first kind of concrete example. Okay, it's a private multi-agent estimation. So let's say that there are K hospitals, each with some private patient data. And there might be some patients that are common between hospitals. So that's possible that some people went to one hospital for some time and then another one, or whatever. Maybe there's a data sharing agreement between 2 hospitals. So there might be common data between these hospitals. And let's say that all these hospitals, the city wants to estimate some quantity like theta star. Okay, let's say that's the treatment effect of some drug among a subpopulation, or something like, let's say, the proportion of teenagers with some disease. They want to estimate this, but they want to do it privately. There might also be some relevant public data. So for example, some census age distributions for the city or something like that might be also available. So each hospital is going to combine all of this information and produce its own like locally private confidence set for theta star. Okay, so maybe you don't know the definition of local privacy. It's a particular form of differential privacy that tries to maintain privacy at an individual level. And so the hospitals might not want to share this data and leak to anywhere else, or even provide summary statistics, but just provide a private confidence interval and say, well, our confidence interval for theta star is this quantity, and each hospital might provide this. And now the question is, if you're an aggregator like a city or a state or whatever, how do you combine these dependent confidence intervals? Because there's some amount of data that's shared. Maybe they all use public data. You don't really know what went into forming these confidence intervals, and now you just have K of them, and you would like to combine them in a rigorous manner. And a second example is something called conformal prediction. I know that now conformal prediction is taught in several classes, so I'll only give a high-level overview of what it is. Conformal prediction is a wrapper around regression or classification algorithms that aims to provide uncertainty quantification. So you should usually think about prediction algorithms as providing point predictions. So conformal prediction changes that and says instead of making for a new test point X, instead of producing a point prediction, I'm instead going to produce a prediction set C of X, which has the guarantee that the probability that Y, my unknown outcome, lies in C of X is at least 1 minus alpha. And it's able to produce this type of a prediction set under very weak assumptions on the data and on the underlying prediction algorithm. It only needs some kind of exchangeability of the data, and the algorithm just needs to treat the data points symmetrically. But which prediction algorithm should you choose? I mean, for any given prediction algorithm, I can wrap conformal prediction on top of it. But for a new problem that you face, should you use random forests or neural networks or lasso, or what exactly should you use? So suppose you actually have k different prediction algorithms. Let's say that they're trained on the same data, and you're making a prediction on the same next test outcome. You're going to get k different prediction sets given by each of these algorithms, and each of these prediction sets is going to be marginally valid, meaning it satisfies that type of a prediction guarantee kind of averaged over all of your data. And now the question is, well, I have k of these. How do I combine them into a single prediction set? Okay, and so these are maybe two concrete examples to keep in mind. One of them is estimation, so it's a confidence set. The other one is prediction, so it's a prediction set. But both of these are uncertainty sets that we might wish to combine in applications. Okay, so the abstract problem statement is just I have some sets C1 to Ck that are arbitrarily dependent. In both cases, it might be because of shared data or something of that kind. But they satisfy some kind of 1 minus alpha guarantee, either of coverage of an unknown point or coverage of some kind of a treatment effect estimator. And what I want is an output. I want to output a single set C that combines all of these K sets in some kind of black box manner, but nevertheless has, let's say, nearly the same coverage guarantee. Okay, so how do you do this? This seems like such a basic problem that everybody should know the answer, and this should be in 705, but it's not, but maybe it will be one day. Here's two things you can do which are naive, two extremes. So one is you can just say I'll output the union of these K sets. Clearly that has 1 minus alpha coverage because each of them has 1 minus alpha coverage, but it's too conservative, meaning the set is too large. You'll have coverage much larger than 1 minus alpha. Or you can take their intersection, but that has coverage 1 minus K alpha by the Bonferroni rule, and that's too anti-conservative. So if you have K large, then that's actually a meaningless coverage guarantee. So you want something in between the union and the intersection, which is reasonable and has a guarantee. Okay, so here's the first solution, majority vote. Okay, so the majority vote interval is written like that, and all it means is I'm going to include a point in my set if at least half of the intervals think that that point should be in my set. So I'm going to check every point in the space, and if more than half the intervals say that I should include that point, then I do include that point. Okay, so it's just the most simple possible solution, majority vote. But here's a very clean theorem. The majority vote set has coverage 1 minus 2 alpha. Okay, with absolutely no conditions and no asymptotics, no nothing. You get a 1 minus 2 alpha coverage guarantee for the majority vote set. Okay, so that's very clean. That seems to have been rediscovered in different forms in different papers in the literature, and they all have potentially different proof techniques and so on. Here, the theorem is so simple and so clean, and it has a one-line proof. So I decided, like, even though this is a broad audience talk, people can tolerate a one-line proof, and it's the only proof in the talk. Okay, so here's the proof. Let phi k denote the indicator of miscoverage for the kth set. Okay, so it's just a 0 or 1. It's a Bernoulli random variable, which is just 0 or 1 if I miscover the kth set. And note that the expected value of phi k, which is the probability of miscoverage, is at most alpha. Okay, that's by definition of Ck being a valid 1 minus alpha coverage set, the probability of miscoverage is at most alpha. And now we just note that C, which is our target, the thing we're trying to cover is C. The probability that C is not in our majority vote set is equal to, when is C not in a majority vote set? It's not in there when at least half of the intervals say it should not be in there. So which means that when I look at the sum of these 5Ks, at least K over 2 of them said it should not be in there. And so that's how I get the first part. And then I just apply Markov's inequality, which is the first inequality that anybody learns in 705. And so Markov's inequality just says I have a non-negative random variables, the sum of 5K, and that probability is at most the right, 1 over the right-hand side times the expectation. Okay, so that's just Markov's inequality, and you immediately get to alpha. So it's extremely straightforward. It's a very simple proof. It's a very simple solution and a very simple proof. So it should be transparent that this works. There's no particular reason you have to choose a threshold of half. Okay, when it's half, I'm calling it majority vote. But in general, you can just call this a solution by voting. So if a tau fraction of the intervals or sets, the input sets, if a tau fraction of them says it should be there and you keep it with according to that rule, let's call that set C tau. So Cm is the majority vote set, but C tau is when I use a threshold of tau instead. Then if you just follow this proof strategy, you just get that coverage level is 1 minus alpha by 1 minus tau. And this really does interpolate fully between the union, the intersection, and the majority vote. So when you put tau as 0, this is 0 means if anybody thinks it's in there, I should include it, and that's the union, and you get 1 minus alpha. If tau is 1 minus 1 over k, it's greater than 1 minus 1 over k, which means everybody thinks it's in there. That's the intersection, and then you get 1 minus k alpha. And when tau is a half, you get that theorem, which is majority vote. So it really works for any threshold, and you can use any threshold in practice depending on what kind of final level you're okay with. You can do that. Okay, so that's the very first solution. But now we can go a little bit from let's build on from there. So suppose you have some prior information, because you have some idea that certain agents are more likely to be accurate, smaller sets than other agents. Then you can incorporate this knowledge with using a prior distribution W over the agents. Okay, so you just pick weights W1 to WK that sum to 1 and use weighted majority instead. Okay, so I'm defining CW as the weighted majority vote set where you include a point in your final set if the total weights of the people who think that the point should be in there is at least a half. Okay. Sorry.
How do you actually calculate it?
I mean, in the case of intervals, you can quite easily, you just have to check the boundary point. So we have an efficient algorithm in the paper that just sorts the boundary points, and it can only be a union of sets. So in general, if the input sets are intervals, then the majority vote set could be a union of intervals. We'll see in our experiments that it's usually an interval, and more than 99% of our simulated examples it actually is just an interval. But at the worst case, it could be a union of intervals, but it can only change at the boundary points. So you really only have to check at the 2K boundary points whether how many people agree over there. So it's very efficient to calculate. Of course, if the sets are multidimensional, then it's going to be harder. So maybe there's some computational things to do with future work. Okay, so the weighted majority vote set also has a 1 minus 2 alpha guarantee, and it follows kind of the same proof. It's pretty clean. Okay, so now you can ask, maybe how did one think of this solution? It turns out that there's a duality between confidence intervals or confidence sets or whatever and p-values. Okay, so hypothesis testing and estimation, there's some kind of duality. So under the hood is something called Ruger's combination rule, which is interesting. I'll just state it as a fact. So the majority vote confidence set is actually a dual of Ruger's combination rule. So his combination rule said the following. So if I give you k p-values, hopefully people are familiar with p-values. If you don't know the definition, you at least have some idea that they are measures of evidence for testing a null hypothesis. So suppose you have k different p-values. So there are many ways of calculating a p-value, and suppose you calculate it in k different ways. How do you combine them? And Ruger said that, for example, you can take twice the median. So pk over 2. This pk is the kth smallest p-value. It's called order statistic. So pk/2 is the median. It turns out that the median is a sensible way to combine p-values, but the median is not a valid p-value, but twice the median is a valid p-value. And more generally, you don't have to stick to the median. You can take any other quantile and multiply appropriately by capital K over small k. So for example, you can take the smallest p-value and multiply by capital K. That actually corresponds to the like Bonferroni correction. Or you can take the largest p-value, which is p capital K. And that's like the union. And so essentially, you can think of these rules for confidence sets as inversions of these rules for p-values. But it turns out that what we were able to prove in this paper is that if you use randomization, then you can have a strict improvement over Rubus combination rules. Okay, so let's look at that. So let U be an independent uniform random variable that's just drawn independent of the data and everything else. Then it turns out that that the same combination rule, except I look at the order statistic UK, and I have the same factor over there. That's also a valid p-value. And this is always almost surely smaller than the original one because U is almost surely less than 1. So UK is almost surely less than K. And so I'm going to take a smaller order statistic. I'm going to get always a smaller p-value. So somehow this p-value is always smaller than this p-value and it's also valid. So it turns out that somehow like you cannot, this rule is actually admissible, meaning you can't improve it if you stick to deterministic rules. But we found that if you're allowed to use external randomization, then you can actually do something better. And in particular, if you put capital K, what this is saying is that if I look at a random index, then that's actually, if I sort the p-values and I pick a random index, that's actually a valid p-value. That's a pretty interesting fact. So how do we incorporate that idea into randomized voting? Okay, so here, let's say that little u is the realization of a uniform 0-1 random variable. Then independent of all the data, I can define this randomized weighted majority vote set. Okay, so this looks exactly the same as before. I look at the total weight of all the people who said a particular point S should be in my set. And if that weight is larger than a half, that's what I had before. Now I'm saying if the weight is larger than half plus u over 2, then include it in my randomized set. Okay, so this is going to be a smaller set because this is a higher threshold. And so fewer points will satisfy that threshold. But I can have exactly the same coverage guarantee. So somehow, so this set CR that I've constructed is smaller than the weighted set that I had before, but nevertheless, it still has a 1 - 2 alpha guarantee. And the proof uses essentially the same proof that I showed earlier, except instead of Markov's inequality, there's something called randomized Markov's inequality that along with Duda, we had invented last year. And randomized Markov's inequality is this following fact. It says for any non-negative random variable x, the probability that x is larger than u times a is at most the expected value of x by a. So if you see capital U there, if you substitute u as 1, that's Markov's inequality that everybody is taught. Okay, it turns out that if you throw in a uniform random variable that's independent of x, the same statement is still true, but this is a strictly stronger inequality because UA is smaller, is almost surely smaller than A. So I'm making a strictly stronger claim. Okay, so somehow we had never seen this before, but this is true. And you know, so in this earlier paper we showed that hence you can improve Chebyshev's inequality, you can improve Hutting's inequality, you can improve Bernstein's inequality, and so on. So that somehow there's no deterministic improvement to many of these inequalities, meaning that there is no constant you can put into Markov's inequality to improve it, but there is a random variable you can put in there to improve it. And that's true for now there's a randomized Hutting's inequality that's almost surely tighter than Hutting's inequality and so on. Okay, so if you're interested in that, check out this earlier paper, but all we are using here is that there's a randomized Markov inequality, and if you plug that into my proof that used Markov, then you'll see that this set is tighter and yet has the same coverage guarantee as the original set.
Is there some reason you picked a uniform distribution, or can you just pick any other kind of?
Yeah, it works best with uniform. It doesn't seem to work with others. So yeah, you can try offline and see if something else. I mean, actually, it can be stochastically larger than uniform. It doesn't have to be uniform. And in fact, 1 is a special case that's allowed. So this is really a strict generalization of Markov because you can put in 1 there. But uniform is somehow the right thing to do. But maybe this opens up a whole Pandora's box of randomized concentration inequalities where you should use other things. I don't know. We only managed to really make it all work with uniform. And then every single Chernoff bound you've ever seen can be improved, almost surely strictly improved with no loss of coverage. But now you improve it with a random amount. So it's quite interesting and but probably the topic of another talk. Yeah. And here's another alternative. So instead of having a threshold that's actually strictly larger than a half, you can just throw in your threshold as u. So now you just have a random threshold, and it turns out if you just work for the same proof, you get a coverage of 1 minus alpha. So in this case, you're always better than the majority vote, but in this case, you might be sometimes looser than majority vote or larger than majority vote, depending on if u is greater than or less than a half. So, but you get a 1 minus alpha guarantee. Okay, so there's variants of this that you can write out, but the idea is somehow you can use weights and you can use randomization to improve power. So if you have prior knowledge and if you're willing to use randomization, then you can gain significantly. Okay, now you can ask the question, well, what if the sets have different coverages? Okay, so not all experts may actually be accurate. Some may be overconfident and some may be underconfident. You know, you ask them for a 95% set, but maybe they typically seem to just give you a 90% set or a 99% set. So maybe it's not their intention, but they just do that. So you can ask, how does this set perform if the input sets actually have different coverages? And the answer is very simple. So if the set CK actually has coverage 1 minus alpha K, then the probability of coverage is just 2 times the weighted average of these alpha Ks. And so if all the alpha Ks equal alpha, then I get 1 minus 2 alpha. But otherwise, it's very clean. So there's because the proof is so simple, all of these things go through very easily.
How do you learn these WK?
Yeah, that's the next.
Oh,
Yeah. So right now I call them prior weights. So it's like if you have some prior knowledge about the situation and you think, well, I trust this expert more than that AI system, you can give that expert a higher weight than that AI system, you know, or vice versa. But yeah, so now we'll get to the question of learning. Okay, any questions about what's been presented so far? I don't see anything online either. Okay, so I will get to your question soon, maybe in 5 minutes. But here's a conjecture or a hypothesis or an assumption. It'll be an assumption later, but right now it's a conjecture. Here's actually another way to combine these 1 minus alpha confidence intervals into a single one. You just pick one of them at random with probability WK. Okay, so instead of doing my weighted majority vote, you just use that probability distribution to pick a random one CK. And clearly that has level 1 minus alpha because every input one has level 1 minus alpha. So I have a conjecture that majority vote is actually better than random. So which means that whether you use a randomized majority vote or not with weight W, it's actually more statistically efficient, meaning it yields a smaller set than random guessing via W. So somehow random guessing only picks one set, but majority vote is really combining the opinions of everybody. And so there is some sense in which we should expect that it's using the wisdom of the crowd and it's going to be tighter. We don't currently have a proof of this fact yet. So right now I'm just going to call this a conjecture of better than random. And we'll see that this conjecture actually seems to be true in experiments. And I'll show you some experiments now that it does seem to be true, but we haven't proved it yet. It seems like a very sensible thing that should be true easily, but we don't know yet.
And so it's like by small, you mean like in terms of value or like general?
Yeah, exactly. Let's say the intervals by size. I just mean most statistically efficient means size. They are, that's what I'm.
Okay.
Okay, so it seems to be true in experiments. Let me show you a couple of experiments. So the first one is this private multi-party mean extension setting that I talked about. So just to simulate some setting, there were two different scenarios. In the first scenario, we generated nk over 2 points, and each agent, there are k agents, and so each agent got a random n subset of these points. So there are a total of nk points among these k agents, but there's only nk over 2 original points, so there's lots of shared points between these agents. Okay, so they take these n points and then they construct some confidence intervals and they submit them, and so that's scenario 1. And then scenario 2 is just a different type of dependent structure where n points are generated for the first agent and every subsequent agent is assigned a fraction of some of the points from the previous agent and some fresh points. Okay, so just a different form of dependence. And so what this table is showing, it has 4 columns. The first column, there's different scenarios over there. The first column, agents, is in the first row is the average width of the confidence intervals of those agents. Okay, so in this case, we used a particular non-asymptotic, confidence interval that is differentially private. So it tends to overcover. So what you see in the second line are the coverages. So the width is 0.32 in this case. The intervals and the coverage it's over covering because it's a conservative interval, so you get 98% coverage and so on. So those are the agents. When you do majority vote, you do get something smaller in width. So it's like 0.30, it's smaller, but larger in coverage. So it might seem almost counterintuitive. How can you get a smaller set but have larger coverage? But the idea is that somehow majority vote is increasing your accuracy. So even though it's kind of ruling out bad points and it's focusing its energy on good points. So it's really honing in on the right region. So it's smaller, but because it's honing in the right region, it's also almost always covering the right answer. So somehow it's smaller, but it's over covering. The randomized majority vote is significantly smaller in width. So, majority vote in this case, got a small improvement in width, but randomized majority vote got a huge improvement in width. And there's mathematically no difference in coverage, but of course empirically you will see a difference in coverage. It's a tighter set. So it's like 97% and so on. And the last column of random vote is just the one where it's not majority vote. I just put in U as the threshold. It's just a random threshold, and the random threshold is no different somehow from the original agents. Okay, so the original agents are 1 minus alpha. This also gives you 1 minus alpha, but it's a combined set. So somehow it's maintaining the same width, but it's a single interval that combines them, but randomly.
How does each agent generate a confidence set?
That's from our yours, mine, and Ian's ICML paper. That confidence interval. Yeah. So from our ICML 2023 paper on differentially private confidence.
Everybody have different sample size.
Yeah, they have the same sample size then, but different samples.
Okay.
Yeah. This is just I didn't want to get into the privacy aspect, but just it's a simulation example to see how these things work. So here's the different, that was for estimation, private estimation. This is a prediction, so conformal prediction with the lasso. So let's say you wanted to run the lasso on your data set, but you don't know how to choose the tuning parameter lambda. So one sensible thing to do would be just let me try many different tuning parameters lambda, and each of those algorithms will output some prediction set, and then I'll combine them by a majority vote. Okay, so let's just see how that does. So I fix the data set and I fix lasso and I only change the parameter lambda. So my different predictors are just lasso with different lambda. And I'm going to produce conformal prediction sets at level 0.05. So what you're seeing over here is on the x-axis is just the tuning parameter. As lambda varies, close to 0 is no regularization and away from 0 is large regularization. As lambda varies, you'll see actually there's a nice sweet spot somewhere in the middle, which is perhaps the lambda that I should have chosen. But I don't know how to do actually model selection because it requires double dipping at the data. So model selection with conformal prediction is somewhat we don't really know the right way to do it yet. So let's say here I just produce all of them and then I take the majority vote. So what you're seeing on the right over here is the majority vote set. And I mean these are the actual prediction intervals. So these are super wide prediction intervals and these are pretty small. You can see the majority vote set is pretty good. It's actually comparable at least to let's say the best fixed lambda that you may have chosen in hindsight, which is not a valid prediction set, but it's at least comparable to that. What you're seeing in red is because the randomized set produces a random set. I've just showed you 2 different instances of this random set. So this random set is always smaller than the original set because my threshold was half plus u over 2. So no matter what u turns out to be, it's always smaller than the original set. So my randomized set is always going to be smaller than blue. So this is when I get 1/3, and this is when I get 2/3. When u turns out to be 1/3 or 2/3. So u is random, of course. So in a real instance, I would actually just run this once and I would just get 1 set. But for the purpose of visualization, I'm just showing you 2 different values of u. Those are the 2 sets you'd get, which are pretty small. This is the other random set, which is where I just use the random threshold of u. And again, when the threshold is 1/3, then it's actually larger than majority vote because it's less than a half. And when it's 2/3, it's actually smaller than majority vote. So, but you just get a random u if you use that. I mean, I would typically use randomized majority vote, but just to show you kind of what you get. So those are and the coverages turn out to be 97% for this one, 92% for this one. Remember, the guarantee is 1 minus 2 alpha, so it should be at least 90%. So you get 97%, 92%, and 96% for this one. So this has coverage 1 minus alpha as expected. This has coverage 1 minus 2 alpha as expected, and this tends to overcover. So even though the guarantee is 1 minus 2 alpha, you tend to get 1 minus alpha actually in practice.
If I'm understanding it correctly here, this is for prediction at a particular point, right? For any given.
Yeah, so there's just one X, I'm just showing you what happened. Like there's just one future X. So for every X, this is, you'd be having a picture like this, yeah.
But instead, I mean, at least in this case, also case, you would probably want to get it for the parameters, right? Like you could get uncertainty sets for the parameters.
Oh yeah, no, over here I'm doing conformal prediction. I want to do prediction. I'm just coincidentally I'm using the lasso and I have a tuning parameter. But yeah, I'm producing a prediction set for a new observation. But yeah, I mean the same thing might apply for.
But then it's a multi-dimensional setting, so that's
Yeah,
why I was thinking. Then the whole done is optimization, right? You can do this for single
Yeah.
scalars, but not
Yeah.
for multi.
Yeah. So yeah, I mean I'm very much interested in the setting of conformal prediction because yeah, a lot of these prediction algorithms, we don't tend to look into the hood and care about their parameters. We just care about their predictions. So I really am just trying to cover Y. So I'm not really trying to learn. I don't think it's really a linear model, and I don't think I want to learn the betas. I just want to use the lasso to predict well out of sample. And so for a new test point X, I need to produce a prediction interval Y, and when this is just one.
But just that if you did that, you would not have to do it for every point, right? If you have it, like even if your goal is prediction, right? You got some uncertainty sets for your parameters, you can then potentially extend that and say what the prediction sets would be, or whatever your confidence set would be for whichever one you cared about, for a bunch of different points, as opposed to doing it for specific points, right?
The advantage of conformal prediction is, like, it's an important advantage that it does not assume that the model you use is correct. And so like I guess I don't want to assume that any confidence set I'll produce for internal parameters of the lasso are actually meaningful in any way. And I just want to produce prediction intervals, and lasso is just what I think will predict well. And I'm doing it just for visualization. I could have conformal wraps around random forests or neural nets or anything else. So, but I agree, you could use this majority vote for anything, including confidence intervals for particular parameters. Okay, so now to Stephen's question, which is, well, this was, all fine for a one-time solution. So if I just have in one shot K sets and I want to combine them into one, okay, this is fine. I can do majority vote, or it's weighted or randomized variants. But can I learn over time which experts to trust? Okay, so and also if the experts are frequently giving prediction sets, for example, making predictions frequently, and we can observe the outcomes, is it possible to somehow get small sets by figuring out which is the right expert, but also at level 1 minus alpha, rather than 1 minus 2 alpha or something else? Okay, so the idea of what I'm going to present next is simple. We're going to upweight good experts and downweight bad experts, but we can also adaptively tune the coverage level that we ask for the sets from the experts, so that we finally combine them to get 1 minus alpha coverage. So instead of asking the experts for 1 minus alpha sets, I'll ask them for sets at other levels, so that my combined set has 1 minus alpha coverage. So I'll explore these two ideas differently because both of them have their subtleties. And I'll first talk about how do we upweight and downweight experts over time. Okay, so the first thing about improving with experience, and so this is important. I'm going to start off in this first case by assuming I have some kind of IID data. The reason I'm saying IID data is just so that I can think of conformal prediction as actually producing 1 minus alpha prediction set. So let's say that these experts that I have, they are actually calibrated, which means that errors are actually 1 minus alpha. All I want to do is learn which is the best expert and have my weight focus on the best expert. So what I want is, as the predictions are made and the outcomes are observed, I'm going to update the weights based on the exponential weights algorithm. Okay. Now there's one very interesting subtlety with the exponential weights algorithm. It does not somehow trivially apply to this type of a problem. Firstly, because our loss function that we're going to end up using, the loss function of the individual sets is not bounded. And if you look at any of the typical proofs of the regret bound for weighted majority, things like that, it might need a bounded loss function, or at least a convex loss function, or something of that kind. But this loss function is just not bounded, and it's unbounded and non-negative. And the second thing is, my majority vote definitely is not an convex combination rule of any kind. It's some kind of weird combination rule. So even if the individual set sizes have just, I look at the size of the set, this majority vote combination rule seems non-trivial enough. So it's not immediate to see whether the guarantees of the majority vote algorithm will go through in our setting or not. So there's some subtlety over there. But at least let's say we want to apply the idea. This is what the idea would look like. Okay, so here's a pseudocode of the algorithm. If you can't see it from the back, I'll just tell you what it is. You know the setup already. At each round, at each time t, I'm going to get k sets, one from each of the experts. Let's say these are 1 minus alpha sets for the moment. So I'm only going to look at the size of the set, not at the coverage of the set. The size is the only thing that matters now. I have an initial learning rate eta, which is some constant I set initially. And I have some weights. Initially, weights are 1, meaning I just have equal weights for all the experts. And my initial loss of all the experts is 0. So all the experts have 0 loss initially. So what I do is at each round, I report the weighted majority set. I can add randomization if I want to. But in this case, these weights are unnormalized. So on my right-hand side, I just have the sum of the weights divided by 2. Just because my weights are unnormalized now. But otherwise, it's just the majority vote set. Then I receive the losses. For every expert, the loss is just the size of the set. Okay, how wide was the set, or what's the volume of the set? Well, let's think of these as intervals. So I just get the size, the length of that interval. And so I update the total loss of that expert by just saying, well, the total size of all the intervals I have so far. And then I have to provide some way to update the learning rate over time, this eta. And then the exponential weighted majority idea is just that the weight is exponential of this learning rate times the total loss of that expert. So if I have experts that are consistently giving me large sizes of sets, then their weights will be exponentially small. I have to figure out what this constant is that I have to set, but otherwise large losses, large sizes of sets means exponentially small weights, meaning in future rounds I'll discount them and I'll kind of focus my energy on people who are giving small sets. So very natural idea. So how do we set this learning rate eta? One idea is, well, you can set it to be a constant 0.1 or something of that kind. Turns out that the performance of the algorithm really depends on this learning rate eta. And we found in the literature a very smart learning rate that seems to work super well in practice. I don't know if this is well known, so I'll tell you, this is what we used and it worked really well out of the box. So this learning rate is called AdaHedge, and it comes from a paper by Dirui et al. In 2014. And they set eta of t in this particular very simple form. It's just log k divided by the sum of deltas at the previous steps. And what are these deltas? This delta is the difference between the hedge loss and the mix loss. The hedge loss is just the hedge loss in the ith round is just the dot product of my weight vector and the loss vector. So loss vector is just what, how wide was each of the intervals in that round, and the weight was how much weight did I put on each expert in that round. So that dot product is just called the hedge loss. This log sum x quantity is called the mix loss. I'm not going to explain from that paper where this comes from, but the difference between this log sum x quantity and just the dot product quantity is this difference between h and m, that's delta. And you said eta is log k divided by. So it's fully adaptive, which means there's no magic constants that come in anywhere. And it's fully data driven, meaning based on the loss and performance of the algorithm, it figures out whether to use a large or small step size. Okay. So let's see, like just as a visual example, how this is doing. So here I just have, just for visualization, it could get too complicated. I have just two prediction algorithms, random forests and neural nets, that are like over here actually, random forests and neural nets, and they're both producing prediction intervals. And I'm plotting over here the hedge loss. There's a lot of figures going on, but eta is 0.1 is just, I just have a fixed learning rate eta, meaning I don't try to adapt it over time. And you can see that it's not doing very well. The hedge loss, the loss that the algorithm is suffering over time is quite large. But if I fix eta as 1, a different constant, then the loss suffered by the algorithm is quite small. So it's very sensitive to this constant. But if I set an adaptive eta, then you can see that it actually does as well as this constant of 1, for example. When we tried many constants out to see, well, it would be nice if it had chosen 1 in hindsight. but how do I know I should choose one? We don't have to know. If you adapt to eta, in the beginning, it's doing something, in fact, slightly even better than one, but very soon it kind of matches what's going on. And if you have, two different algorithms, in this case, in pink and blue, the pink algorithm seems to have a higher loss than the blue algorithm. You'll find that the adaptive eta quickly figures out that it's really the blue one that's better and follows the blue one. Okay, so this is just with two algorithms for some kind of visualization. X-axis is iteration. So very quickly, the adaptive eta is honing in on the better algorithm, which in this case is random forest. If you want to see it with more algorithms, so here's these are different time steps. And now there's 5 algorithms: lasso, linear model, neural nets, random forest, and ridge. Again, connecting, I'm showing adaptive eta with 2 constant choices of eta. And so initially, everything starts off with equal weights. But after 15 steps, our adaptive eta has already figured out that random forest is somehow the best performing algorithm and hones in on that. But eta equal to 0.1 is too slow, and it's kind of getting there eventually. But after 75 time steps, it still hasn't figured that out. And eta equal to 1 was a better choice, but even that somehow after 60 or 75 steps is still figuring out between neural nets and random forest what's going on. But with adaptive eta, it kind of quickly honed in on the right answer, which was in this case random forest. In this IID scenario, random forest was the best one, and you should just follow its advice. Okay, so what can we say? Well, here's a regret found, assuming my conjecture from before of better than random. So if you remember the better than random conjecture, it's that playing my weighted majority vote with W is better than randomly picking one expert with probability W. Somehow so that's the better than random conjecture. Okay, so here's the regret bound I'm going to present. So the regret is the difference between our total loss, which is the cumulative size of our sets that we produce, and the total loss of the best individual expert K star in hindsight, the total sum of the lengths of the confidence intervals produced so far. And this regret bound will only hold if weighted majority is actually better than randomly picking one, which was our assumption from earlier. It looks slightly complicated, but I'll explain the pieces to you. It's not that complicated. So you have a log K factor and a square root and a log K outside. So the K is something you already know. Then there's L star. L star is the comparator. That's the loss of the best fixed expert in hindsight, the total loss of the best fixed expert. L plus and L minus is like the aggregate of the maximum and minimum loss in each round. So if you call L plus at time step T as the maximum size of the interval at time step T, and L minus as the minimum size of the interval at time step T, then capital L plus and capital L minus are just cumulative versions of those over T steps. And so they're just looking at comparing, L plus is larger than L star, and it's just comparing those. So there's some normalization here going on because I don't know the size of the loss range. This is an unbounded problem. And so this S term over here is the largest loss range, which means this it's the maximum S1 to ST, where S is L plus minus L minus, which is the difference between the largest loss and the smallest loss, which is called the loss range. And capital S is the maximum loss range. And so it's a non-standard regret bound because we have non-standard losses which are unbounded, but it turns out it at least scales with the realized losses. So even though things are unbounded, it doesn't depend on, well, it can't depend on the maximum because that's infinite. It really depends on the scale of the losses that we've actually encountered in our algorithm, which is reasonable, has kind of a logarithmic dependence on the number of experts we're combining. So reasonable. So things of that kind. So anyway, it's a reasonable regret bound. I won't stare into it too much, but it does only hold if our conjecture is true. And so if anyone has any idea how to prove that our conjecture is true, I'd be happy to hear it. Okay, now the second part, so the first part I just said, if the data was IID and everyone was producing 1 minus alpha prediction sets, things are fine. I can now use my exponential weighted majority algorithm with this adaptive step size, and I can learn the best expert over time. But what if the data is shifting and drifting, and these experts are actually, some are overconfident and some are underconfident? Then how can we adjust to this? Okay, so essentially the previous algorithm, we were able to focus on the size of the set because we assumed the coverage is the same for all of them. But if some people have consistently small sets and they are consistently undercovering, then you shouldn't be focusing on those people because you'll put all your energy on a very small set that completely undercovers. That's not useful. So the previous algorithm is only useful if you can somehow maintain 1 minus alpha coverage. So what if, you have these distribution drifts and shifts? Is it still possible to combine them to yield small sets? And so we'll show that the answer is yes, by wrapping around an existing algorithm by Gibbs and Candace that they've been exploring over the last 2-3 years. That's called adaptive conformal inference. And adaptive conformal inference was built for exactly this setup to adapt to these kind of distribution shifts. So now I'm going to really focus on the conformal inference setup, because if you have confidence intervals that are miscovered, I really don't know what to do with them. But for prediction intervals, we know how to adjust conformal inference to adapt it to the case where the distributions are shifting. So adaptive conformal inference has a very simple idea. It says that instead of outputting 1 minus alpha prediction sets, it'll instead output 1 minus alpha t prediction set, where it'll change alpha t in each round. It'll start off by saying, well, in my very first step, I don't know anything about the world, so I'll just set alpha 1 as alpha. So in my first round, I'll produce a 1 minus alpha prediction set, or I'll try to produce a 1 minus alpha prediction set. But I'm going to adjust alpha up and down based on what actually happened. So I'm going to get this feedback phi t, which is this Bernoulli indicator of whether the outcome yt actually was contained in my set or not. So whether I miscovered or I didn't. And essentially I take a stochastic gradient step in alpha, the coverage level. So if I miscovered, then I decrease alpha. And if I covered, then I increase alpha. And so you should think of this as some kind of stochastic gradient step in the coverage level. Okay. And so it's a very interesting idea. So at every single step, I kind of just change my coverage level as I go along. And Gibbs and Candace prove that the average coverage that you do get will actually approach 1 minus alpha in the limit. So you should think of this like a control strategy, like an online control problem, where the world is shifting and drifting, and I want to just maintain 1 minus alpha coverage. So sometimes I'll have to, undercover and overcover so that I maintain 1 minus alpha coverage overall. And so they show that under relatively weak assumptions on the distribution drift and shift, you do get this 1 minus alpha coverage over time. Now, this, of course, is for a single prediction algorithm. I have one prediction algorithm like random forest, and then I can adjust this alpha level over time for it. Now, how do I, what do I do if I have k different algorithms running at the same time? Okay, so we call this conformal online model aggregation, so COMA. So there's two different ways to combine the ACI algorithm with our dynamic merging algorithm, this exponential weights type of algorithm. So the first method is completely uncoordinated, which means that we just run k different uncoordinated ACI algorithms, one with random forest and one with deep nets and so on. Each of them is using the adaptive conformal inference on its own, maintaining 1 minus alpha coverage on its own. And we just wrap our exponential weighted majority algorithm on top of it. We have just k predictors. Each of them is roughly giving us 1 minus alpha prediction sets, and we figure out what the weights are that we should have over them. So this is an uncoordinated method, and that's fine, and we'll get 1 minus 2 alpha coverage. But an interesting other option is actually a coordinated method, which doesn't use our exponential weighted majority just as a wrapper. So we have k different adaptive conformal inference algorithms running, but we provide them feedback. Remember that each algorithm changes its alpha level based on feedback. Did it miscover or not? But the feedback that we provide to them is not based on whether their set miscovered or not, but whether the majority vote set miscovered or not. Okay, so we provide them exactly the same feedback and whether the majority vote set covered or not. And now what happens suddenly is that instead of the individual algorithms approaching 1 minus alpha coverage, they're actually getting feedback not about their performance, but the majority vote set. So the individual algorithms will behave in such a way that I get overall 1 minus alpha coverage for the combined set. So I don't actually have to do any randomization or any such thing. I'll just get 1 minus alpha coverage if I do this kind of coordinated feedback where my majority vote gives feedback to the ACI algorithms.
Is it the weighted majority with the weights are changing?
With the weights are changing,
Okay.
exactly, yeah. But just I form the set, I do the weighted majority set where I do this exponential weighting and so on for my k sets. And then the weighted majority set either covers or it does not cover the output, the actual Y. And I provide that feedback to the individual algorithms rather than the performance of their own sets. And so this subtle change actually improves performance quite a lot.
Asymptotically over time? What does asymptotically mean here?
It's the same, Gibbs and Candace proved that under distribution shifts and drifts, this algorithm of trying to control this alpha does give an average coverage of 1 minus alpha in the limit, under even though distribution is drifting and shifting.
As T go to infinity?
Yeah.
Okay.
Because I mean, if you have IID, then there's no problem. Every method gives 1 minus alpha coverage in finite samples. But when you have distribution drifts and shifts, you can't get 1 minus alpha coverage in finite samples. And so they show, well, at least you can get 1 minus alpha coverage asymptotically. And you don't need to know the drifts and shifts, you just control your level of alpha. Okay. And what we're saying, if you have k different algorithms, and they're each controlling their level alpha, the way you provide feedback to them is one of two types. Either you provide feedback on their own performance, and this is like just treating our exponential weighted majority algorithm as a wrapper, or you provide, feedback about the coverage of the majority vote set, the weighted majority vote set, and in that case, their guarantees will give us just a 1 minus alpha guarantee as so and this is somehow the right thing to do.
A small question here, like the majority vote, does it include itself or like the total group? Or just like everything else without?
So I have k sets that I'm getting, one from each of these algorithms, and then I just apply my exponential weighted majority algorithm I described, which is I have weights for each algorithm, I do weighted majority, but these weights are being updated in each round.
See,
Yes. So we can see, here's an example of this running in practice. So this is predicting electricity transfer. So the data set is one where we're in Australia and there's two states, Victoria and New South Wales. And every half an hour, electricity is transferred between Victoria and New South Wales. And so we're trying to predict in the next half an hour interval, how much electricity is going to be transferred between these two states. And the covariates that we have are the price of electricity in New South Wales and Victoria, and the demand of electricity in New South Wales and Victoria. Those are the covariates that we have, and we're just trying to predict in the next round how much electricity will be transferred. So we're producing a prediction set as we go along. But it's clearly non-IID data. This is some time series where I'm producing, where the data is definitely drifting and shifting over time. So what you're seeing in each of these individual plots is, if I fix a particular method, like let's say I want to use a linear model, that's what I'm going to use for making predictions of the electricity next round. If you don't adapt your alpha level, then your coverage will fluctuate a lot. Like it'll drop down 80%, it might go up to 95%. But basically your coverage level is just determined by the data. If you don't adapt your alpha level. But if you do this adaptive conformal inference and you actually adapt your alpha level over time, you can get a coverage level that looks pretty much exactly like 95% your target level. So this would be for the linear model, you can get it. And then you can say, well, what if I wanted to use ridge? Same thing. Well, if you don't adapt it, it's not so great, but if you use adaptive conformal inference, it's good. And again, if you use lasso, it's good. Here I'm only showing the coverage levels. The width of these prediction intervals will differ. But the point is that adaptive conformal inference can ensure that each of them is really giving you kind of a 1 minus alpha confidence, prediction set. Now, I want to say, well, how do I combine these? Which ones do I pick? Maybe one of these is actually better than the others, and that's what I should be listening to. Can I learn this over time? Answer is yes. So if you use let's say our randomized weighted majority algorithm or our weighted majority algorithm, then you don't get coverage at the nominal level. You get, it seems to slightly overcover. You get, slightly more coverage than you had wanted. And so the two curves over here are the higher curve is weighted majority and the lower curve is randomized weighted majority, where I'm doing this exponential updating and I'm penalizing you based on your loss so far and so on. Okay, so this is what it's doing, but this is the first method, which is uncoordinated. So I don't know the exact coverage level that I'll get. So the individual methods will get 1 minus alpha, but my combined level has a guarantee 1 minus 2 alpha. But in practice, I don't know exactly what I'll get. It seems like I'll get around 1 minus alpha. But in the second method, where I give feedback to the sets, not about their own performance, but about the majority votes performance, you'll get 1 minus alpha. So you can do this model aggregation online. In this case, it probably focuses on one of them. Let's say random forest. It just kind of says random forest seems to be doing better. And you get, so it'll focus on the best, meaning the smallest one producing the smallest sets, but also you will get 1 minus alpha coverage. And this is despite it being a time series problem where there's no IID structure and so on. So it seems to work reasonably well in practice.
So it's 1 minus alpha over all time steps.
So what you're seeing over here is actually local coverage over 200 steps. So for every 200 steps, at any individual step, it either covers or it doesn't cover. So you'd just be seeing zeros and ones. So I'm just averaging this over 200, the most recent two, like, 200 window, 100 plus or minus, and that's what you're seeing. So you're really seeing that it's giving you around 95% if you wanted around 95%, you're kind of getting it. But if you didn't do any adaptive conformances, then your coverage level would fluctuate much more. Okay, so the idea somehow adaptive conformances does work well with our model aggregation scheme of exponential weighting and so on. Okay, so let me summarize. I know I'm basically just have a few minutes left. So we proposed randomized and weighted variants of majority vote, which I think should be textbook material. How do we combine uncertainty sets? Well, majority vote. We showed how to extend these majority votes to online settings, and in particular performing conformal online model aggregation for producing prediction sets, even in non-IID settings that have coverage 1 minus alpha and yet focus on the best predictor. And the paper also has other extensions. So beyond coverage, so you say, well, I don't necessarily want to measure the quality of my sets by coverage. I want to measure them by some other bounded loss function. So this in the literature is called conformal risk control. And so we have an extension of these ideas to conformal risk control. And some next steps, for example, are proving this better than random conjecture, proving that these methods are actually admissible, meaning you can't actually improve them, and maybe other applications to other settings that you can think of. So maybe I'll stop now, take questions, but also suggestions on where one might take some of these ideas. Thank you.